Hello and welcome back to Differential Equations Chapter 7 tonight. For one last time, yes. So we are talking about the equilibrium points, and we're talking about stability of these systems. So what we are looking for are technically, in the eyes of the first order differential equation, you are looking for critical points. And you know that the critical points are calculated by setting your derivative equal to 0. Now, if you have in your, let me just get this thing, okay? So if you have your differential equation dy dt or dx, whatever, equal to, let's say, x squared, see, I need the dx dt, so I can do x squared minus 4x. There we go. To find the critical points, in this case, you would set x squared minus 4x equal to 0. You can factor x to get x minus 4 equal to 0, from where you get two critical points, two equilibrium points, x equals 0 and x equal to 4. Right? All right, so what do we do with this? Right? You can solve this differential equation by separation of variables. You can get the curves, right? And then you look at the behavior of those curves around critical points. So in certain cases, you are going to have the solution curves to go towards the critical point, and in some cases you're going to have them go away, diverge from it. So if you are able to, should I say in quotes, contain the solutions around critical points, they're stable. And if they are divergent, so going away, they are unstable, because you have two states. You can have a two-dimensional solution because you know that the solution is a function in terms of t or y in respect to x and so on, so it's a 2D solution. You can have some solutions spiral in, and you can have solutions spiral out, or you can have them to be parabolic function or sine function and so on. So stability of the points will depend on the solution. So now, trying to see if we can all right, so let's see. So critical points. So you will be obtaining these points by setting them equal, right? Setting the forcing term equal to 0 and just computing the algebra. What else? If you have a system, it works the same way. So let me pick a problem that is going to have something that I can quickly, I have to do it quickly, but except the system is a little bit harder to solve because you have two equations, two unknowns, so you have to grind through that. So this is from 7.2. You have dx dt is equal to 2x minus 2y minus 4, and dy dt is equal to x plus 4y plus 3. So, to find the points, we take 2x minus 2y minus 4 equal to 0, and x plus 4y plus 3 equal to 0. Now, 2x minus 2y is equal to 4, and x plus 4y is equal to negative 3. Divide the top equation by 2, and then subtract the equations. So I have x minus y equal to 2, and x plus 4y negative 3. Subtract. What's up? Did I do okay? So, when you subtract, so equation 2 minus equation 1, we have x minus x is nothing, and then 4 plus y would be 5y equals negative 5. So y is equal to negative 1. And then x would be 1, right? So the point is 1, negative 1. And that's the only point that I have. So I hope I did all of that correctly there. I think. Now, we also, in addition to this, have the cases where x is equal to 0, y is equal to 0, and we compute that. So x equal to 0, and we have the equation 2x minus 2y minus 4 equal to 0. So when x is equal to 0, negative 2y is equal to 4, and then y is equal to negative 2. So that creates a point 0, negative 2, also to be considered. And then y equal to 0, in the first case, is going to be 2x minus 2y minus 4 equal to 0. I'll give you, let me just calculate this. So y equal to 0, that's a 2x equals to 4, x equals to 2, so there is a 2, 0 point. And then for the second equation as well, I should have, I don't know, maybe the blue arrows will make sense, and then purple arrows on this side, I don't know. X equals 0 gives me 4y equals to negative 3, y is equal to negative 3/4. And then y equal to 0 for x plus 4y plus 3 equal to 0, from where x is equal to negative 3. So over here I have a 0, negative 3/4 as a point. And maybe I should box these so we can find them quickly. And then negative 3, 0 over here.
So you have to do it 4 times?
Well, in this case it's 5. Because you have x equal to 0 for the first equation, x equal to 0 for the second equation. Okay. Calculate y's. Y equal to 0 for first, y equal to 0 to the second, so that's another 2 equations, right? And then the fifth one is to solve this system of equations, right, which gives us 1, negative 1. So we have 5 points that we get to consider.
So this is when the derivative is equal to 0 and both functions equal to 0?
Yes.
Where were the derivatives equal to 0? Oh, you already
the derivatives equal to 0 is the system of equations. right?
You did 2 minus 1 there?
2 minus, yeah, equation 2 minus equation 1.
2 minus 1? Oh, it was 5y. What'd you do? You just...
5 minus minus y is 5 plus y.
The minus 5 is the minus.
Mm-hmm. Yeah, so and you're not going to have, obviously, graphing utility to to graph the phase planes. So that's another. Trying to see if we can find, but I can't find the example. So yeah, just let's leave it here. You know how to find all the points, and then we'll deal with the rest. Well, you will deal with the rest in your next course. Yeah, 7-6 chaos section on chaos. Yes.
We don't even know what kind of equilibrium is.
Stable, unstable, or what's the other one?
Well, without solving and getting the phase plane. Yeah. So we'll deal with that. I mean, if it arises. All right, let's restart for the review.